Hello and welcome back to the channel. Today we are going through exercise 2.14 from the Art of Electronics, and in this exercise we are going through a BJT amplifier or a common emitter amplifier, and we're looking at the feedback effect of the emitter resistor. However, the main focus on this is basically looking at the temperature effects on the PN junction. So let's get started. So for exercise 2.14, we need to show that the statement above the question is true. And the statement says, the problem is that the emitter voltage of only 0.175 volts will vary significantly as 0.6 volts of base emitter drop varies with temperature, which is basically minus 2.1 millivolts per degree C. Since the base is held at a constant voltage by R1 and R2, for instance, you can verify that an increase of 20 degrees C will cause the collector current to increase by nearly 25%. So what I'll do is basically go through how to show this statement is correct, and I'll briefly explain the circuit as well. So starting with the circuit, this is basically a NPN amplifier that has been described in the question. We have our NPN BJT over here. We have some biasing resistors, which the values haven't been defined, but the base voltage has been defined. So you can set these two to achieve this base voltage over here. We have a AC coupled input. So basically all the DC is filtered out. Obviously these and this components over here form a RC filter, which you can calculate the cutoff frequency for this low pass filter if you want to. We have a resistor over here, R3, which is basically the collector resistor. And we have some resistance over here, which is basically RE, or the emitter resistor. Now for the circuit, we have 20 volts power supply, and the circuit has been set up that we achieve 1 milliamp of quiescent current. So that is the current basically when there is no input signal or the input signal is zero. So you can imagine that this point over here, which is the biasing point of 10 volts, is held at 10 volts. So then 20 volts, which is on the power line, minus 10 volts, so that you have 10 volts across this resistor over here, and 10 volts divided by 10,000 ohms gives us 1 milliamp of current. Now the gain for this circuit is given to us as 50, which we can calculate using this equation over here. So if you plug in these numbers, basically 10,000 on the top part over here, 25 is from our internal RE calculation, that's small e. So that's basically the intrinsic resistance of this emitter junction, which gives us 25 to plug in here, and our RE, which is the capital E, which is this resistor over here. Now, if you put those numbers into here, you basically get a gain of 50 on this, which is what is been given over here, and it's also been described above the question. In this circuit, the resistor RE is connected to the emitter of the transistor. But what does it actually do? Well, it plays two very important roles. It reduces the gain of the amplifier, and it provides negative feedback to improve the overall performance. Now, reducing the gain might not be a desired thing, but it does help you control the gain of the amplifier if that's what you need to do. Now, looking at this equation very closely, without RE, which is the capital E over here, the gain would depend on the load resistor and the transistor's internal resistance RE. But when we add the emitter resistor, which is basically R4 over here, the total resistance at the emitter junction, basically from over here to down here, increases, which lowers the gain or lowers this value, as you have a larger denominator over here. I also said that the emitter resistor will provide negative feedback. Think of the transistor like a device that controls how much current flows through the collector. However, that current is controlled by the voltage that appears between these junctions over here, which is basically base emitter. The voltage difference between the 2 points is what drives the amplification. The voltage from the base to the ground is the input signal, as you can see over here, assuming you can ignore this in that you have high frequency signal here relative to the RC filter. The voltage from the base to the emitter, basically this voltage over here, is our input signal minus the voltage that appears on this resistor over here, which is basically IE, or the current to the resistor times the resistance itself. Basically, we are looking at Ohm's law again. So the voltage is created on this by the emitter resistance, and by subtracting that portion from the input signal, we are basically providing net negative feedback. And in this case, the negative feedback will help to reduce distortion and increase input impedance. In the book, it says that the negative feedback will help improve linearity and stability as well as the input impedance that I mentioned before. So yeah, check it out because it's quite important to understanding NPN transistors and amplifiers. So now let's get on to the question. We're basically going to be using this information over here to try and answer this question. So I'm going to split the answer or the solution into two cases. Firstly, I'm going to look at the nominal case where there is no temperature change. So you can ignore what the temperature actually is. So let's pretend that it's 21 degrees. Our VB is set to 775 millivolts, which is basically the base voltage. Our VBE, which is the voltage that appears across the base terminal of the NPN transistor and the emitter terminal, and that will be 600 millivolts nominal. Now, as I said before, the temperature change is going to be 0. So plugging in our VBE voltage and minusing the VBE voltage change due to the temperature, which is basically 0, we have a VBE voltage of 600 millivolts at this case. Our RE is 175 ohms, so we can calculate what VE is going to be because we know VB is 775 millivolts. We know VBE, which is down here, is 600 millivolts. That gives us a VE voltage or the emitter voltage of 175 millivolts. From there, we can calculate our emitter current, which is basically Ohm's law again. So we're doing voltage at the emitter divided by the emitter resistor, which is 175 ohms. So you get a emitter current of 175 millivolts divided by 175 ohms. So that's 1 milliamp flowing down the emitter resistor. Now for case 2, we're going to simulate a temperature change of 20 degrees as what's written in the statement and the statement that we need to prove basically for this question. So starting with our starting point, which is basically the input voltage, we have a input voltage of 775 millivolts, which is not affected by the temperature. The VBE voltage at the nominal temperature, so in our case, let's say 21 degrees, was 600 millivolts. If we added a temperature change of 20 degrees, our new VBE, which is the base emitter voltage, would reduce by 20 times minus 2.1, which would give us a new base voltage of 558 millivolts. Now, I believe this temperature would go down, so ignore the minus sign. So as the temperature goes up, the voltage drop across that junction will go down as typical what happens with a PN junction diode. Now, similar to before, our resistor at the emitter is still 175 ohms. We just have a lower VBE voltage. We can calculate the voltage at the emitter junction, basically 775 millivolts, which is our input, minus 558 millivolts, which is our VBE voltage, which gives us a emitter voltage of 217 millivolts. Now, similar to before, we can calculate the emitter current, which is basically the emitter voltage divided by the emitter resistance, or the resistor at the emitter, not the intrinsic emitter resistance. So that's 217 millivolts divided by 175 ohms, which basically gives us a 1.24 milliamp current in this case. Now, if you remember to case 1, we had a 1 milliamp current, and in case 2, we have a 1.24 milliamp current flowing in that direction. So going from 1 milliamp to 1.25 milliamp or 1.24 milliamps gives us a nearly 25% increase in the collector current, which is basically what the statement said. So we've shown using the temperature change that the statement is correct. We are basically ignoring IB in this case because generally is very small compared to IC and IE. So what we are saying is that IE is approximately equal to IC and we can ignore IB. Now IB would add a little bit more current to IE, but that doesn't really matter because we're going on approximates here anyway. Now, just going back to the circuit, we can look at where the IE current, IB current, and the IC current is flowing. So basically, we have 1 milliamp flowing down this direction all the way down through RE for case 1. We basically have 600 millivolts from here to here for case 1, and that basically gives us 175 millivolts over here. So we have 775 over here from the question minus 600, so we get 175 millivolts over here. Now, using Ohm's law, we calculate the current flowing down. So that's basically V divided by R. So 175 millivolts divided by 175 ohms gives us 1 milliamp of current flowing in this path over here. Now, this current is not exactly equal to this current, but it's pretty close and we're working on an approximate anyway. So IE would also have the current flowing from this direction. So IE would be equal to IB, which is the current in here, plus IC, which is the current down here, but we're ignoring that for the solution. Now for case 2, the only thing that's happening is that this voltage, which is the VBE voltage, is decreasing by 2.1 times 20 degrees. So 20 degrees is the temperature change, and the base emitter voltage decreases by 2.1 millivolts per degree C. So you get a larger voltage here because you get a smaller voltage drop here, as this will stay fixed, or we're assuming that this will stay fixed. So a larger voltage here means that we have more current flowing through this direction. So that's all I have to share with you today. Thank you for watching. If you like the content, don't forget to like, comment and subscribe. Thank you for watching. Bye for now.